اوكي. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Your Excellency, President of King Fahd University of Petroleum and Minerals, Dr. Mohammed Al-Saggaf, distinguished speakers, esteemed colleagues, ladies and gentlemen, Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, good afternoon, and good evening wherever you are in the world. My name is Dr. Osman Al-Hammouz from Chemistry Department. I'm an associate professor at KFUPM. I am humbled and honored to welcome you to the first symposium conducted by the College of Chemicals and Materials entitled Innovative Materials for a Sustainable Future. On behalf of the organizing committee at the college, I would like to thank our distinguished speakers from all around the world that will enrich us with their knowledge on the recent developments in innovative materials that will sustainably shape the future of our lives. Allow me to give the floor to our president, Dr. Mohammed Al-Saggaf, to inaugurate this symposium. Welcome everybody. Dr. Mohammed, تفضل.
بسم الله الرحمن الرحيم. الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Distinguished participants in this important symposium, those participating as speakers and those participating as audience, as well as esteemed colleagues and organizers of the symposium, including the KICS team, of which we are very proud, and the College of Chemicals and Materials, of which we are even extra proud. Given the level of the speakers and how important and distinguished they are, I think it is to be expected that my address is going to be an eloquent one. Unfortunately, I have to disappoint you. It will not be. I thought to say something from the heart rather than something scripted and seemingly smart and intelligent. I think coming from the heart is better. So I'd like in this brief introduction, I think in fact the organizing team has given me ample time. I perhaps will not use all of it. Talk a little bit about KFUPM and talk about the college and talk about materials and chemicals and sustainability. KFUPM has been on a very important journey of transforming itself into a world-class university that produces research and academic activities that are useful to humanity, that has an impact on the way we do things, that improves the human condition, and that amplifies its contribution to the nation and to the globe at large. We have been doing many things and very, very busy over the past couple of years. We changed all of our curricula to be based on what we call the AI plus X platform, such that you first become an expert or at least activated and knowledgeable in artificial intelligence and related disciplines before you embark on your major. We have applied this overhaul to all majors without exception. We then introduced a suite of subspecialties that we call the undergraduate concentrations, and a suite of one-year non-thesis master degrees whose aim is to activate the professionals in society and allow them to become active members of the economy who are able to launch new ventures or amplify their contribution to their companies and organizations wherever they are. To date, we have launched 38 undergraduate concentrations and 32 of these new master degrees in topics ranging from artificial intelligence to cybersecurity to non-metallic materials to petrochemicals and refining, and many to polymer science and engineering, and even futuristic things like quantum computing and hydrogen mobility and so on. And once we were done with this, we focused on the research program and we overhauled it in a way that would make it truly interdisciplinary. And we launched or relaunched 20 new centers. And one of them is advanced materials, but there are many other ones like membranes and water security, intelligent mobility and logistics and hydrogen and energy storage and so on. And as you can see, all of them are thematic rather than disciplinary. We want to fuse the disciplines together, melt the boundaries, because we believe that true knowledge is created at the intersection of disciplines. Truly, if you are just within your discipline, very quickly you will saturate, it will be very difficult to innovate. I know this. I hail from the discipline of geophysics, and I have always said, what can I do in geophysics? I will not be solving the wave equation again. It has been solved over 100 years ago and so on. But when I combine it with knowledge of artificial intelligence and knowledge with wireline logging, spectral decomposition, and spectral modeling, electrical engineering, and so on, then something can happen that can be of use to society. So this has been our mission, and we culminated this effort by redistributing and rearranging all the departments such that they belong together in a way that would enhance this ability to do interdisciplinary work. And hence was created the College of Chemicals and Materials, incorporating chemistry, chemical engineering, material science and engineering, and bioengineering, and in a way that so far we see as quite successful. In fact, proof of which is today's symposium, because it could not have happened, definitely could not have happened in the way it is happening now, in the format that it is happening now, without this goal to fuse the different disciplines together. And I cannot, I want to be very honest and transparent, like any other organization. When you have siblings close to each other, sometimes this develops into territorial disputes, and so chemistry and chemical engineering would quarrel a little bit on the boundaries and what belongs here. Is catalysis chemical engineering, or is it chemistry, and so on? And by putting things together, I think everybody becomes part of the same household, and many of these turn from quarrels into seamless collaboration and cooperation. And of course, it is a long journey. We have just started, so we cannot say that it will not be without growing pains. So we're very glad with what you have done. Now, material in particular is very important. Material is life. We are built from material. We use material to build things. Materials can be a blessing. Materials can be a curse as well. They can be a blessing if they are developed well and designed well and used well in a way that would make them sustainable, reusable, recyclable, all the RE things that would actually allow us to benefit from material, because it will just be insane to say, I will not use the material. No, use the material, but modify it, work on it, evolve it, pivot it into something that would allow us as humanity to achieve the intended objective and the use of this material, but in a way that satisfies other constraints that we need to satisfy as well. Most importantly, a sustainable way going forward with our lives and with our plans. And because of this, the importance of material, the field is very wide, it is very broad, and it is very exciting. Really, yeah, it's very exciting. From using materials in construction and to extend the longevity of buildings, to using them in absorbing carbon dioxide or converting it into a carbon fiber, but in a way that would cut the cost substantially by an order of magnitude, to using materials that would withstand the harsh environment of the fields, whether they are petroleum fields or other fields, and creating materials that would withstand the harsh environment of the body itself if they are designed to be utilized inside the body, whether replacement of veins or expanding them or supporting them, or down to material that can be utilized to manufacture artificial hearts, to material that can be infused with other things like electronic textiles and material that would get its energy from the body and tell us about what's happening in it, to material that is smart and would, for example, tell us whether food has spoiled or has not, and therefore prevent us from wasting millions and millions of tons of food that is perfectly edible, or consuming food that has already spoiled despite an expiration date that has not occurred yet, and so on. So materials really represent life, and to the extent we can do something in material, it is not just research, it's truly research aligned with what we want to do at KFUPM, and that is to improve the human condition. Because if you want sustainability and you say, I'm not going to use material, then this is not improving the human condition. And if you use material in an unsustainable way, again, you are not improving the human condition. So we are very excited. We have already a center dedicated, the Interdisciplinary Research Center for Advanced Materials. We are creating a new consortium for materials to be used in a sustainable manner for a sustainable future. And we are very glad that we have like-minded scientists and engineers and collaborators from around the globe participating with us today in this exciting symposium and exciting journey, and allowing us to turn thoughts and wishes into actual deliverables, into actual research that can manifest itself in products and material that would indeed lead to a sustainable future. So, like I said, I am not going to use all my 15 minutes, though I think I used 90 or 95%. Still, that's not bad. I welcome you again. I would like to thank you. I wish you a very useful and interactive and beneficial, and most importantly, enjoyable symposium. Thank you very much.
Thank you, Dr. Muhammad. Thank you very much for this very nice talk. Okay, before we start, I would like to just give some few points about the regulations. So we will allow the speakers to give their full talk. After that, or during that talk, if you have any questions, you can post it on the Q&A, or you can raise your hand at the end of the session. So please, all of you, allow me to welcome Professor Omar Yaghi. I don't think he needs any introduction because he's well known. Professor Omar is the James and Natalie Tretter Chair Professor of Chemistry at the University of California, Berkeley. He has pioneered several extensive classes of new materials, and he has also created a new branch in chemistry, which is called reticular chemistry. This chemistry has yielded materials with applications in hydrogen storage, carbon capture, and harvesting water from desert air. Also, reticular chemistry is being practiced in hundreds of research labs over 100 countries. He has published more than 330 scientific articles and is considered to be at the very top most cited chemists. He's a member of the US National Academy of Sciences, and he has been honored with multiple awards, some of them like Prize in Basic and Engineering Sciences, the Medal of Excellence of the First Order bestowed by the King of Jordan. Also, he has been given the Prince Sultan bin Abdulaziz International Prize of Water, the Mohammed bin Rashid Medal of Science of United Arab Emirates. He has also been given the Royal Society of Chemistry Sustainable Water Award, United Kingdom, and Vinvuture Prize for Emerging Fields in Science and Technology. So please welcome with me Professor Omar Yaghi, that I consider as a mentor and also a brother. Please, Professor Omar.
Thank you, Dr. Osman, for that wonderful introduction, generous words, and indeed, I consider you a friend and colleague. It's been a pleasure to know you, and it's very nice to see my colleagues at KFUPM. Thank you, Dr. Othman, for the organization of this, for all your efforts on this important topic. I also just want to thank Dr. Muhammad Al-Saggaf for his leadership, vision, and dedication to making KFUPM a force in advancing knowledge in the kingdom for the benefit of the kingdom and the benefit of the world. It's, I think KFUPM is very fortunate to have him as leading at the helm this wonderful institution. And I am also honored to be associated with KFUPM. Today, I would like to talk about materials and devices for a sustainable future. I intentionally put this title here in this way to emphasize the translation of basic research in materials into devices that ultimately can address the issues that we are facing in achieving a sustainable future. I always like to look up the meaning of words in the dictionary. I enjoy reading the dictionary. It's fascinating to look at the meaning of words. And if you look at the meaning of the word sustainable, you find this. Okay, causing or made in a way that causes little or no damage to the environment and therefore able to continue for a long time. It doesn't sound very ambitious. You know, the word little appears, little or no damage to the environment. It's not terribly ambitious, but that's because little changes that we make to our environment really have effects, large effects on everything else we do in this complex climate or complex issues that we face in sustainability. What I really want to say here is that if you look at this definition and you think about how much science could be done under the umbrella of sustainability and what kind of fantastic scientific problems could be investigated, it transcends all divisions of field and divisions of study. And this is a fantastic field to enter because it combines our basic knowledge in various fields with engineering, with computer science, even with the humanities and the social sciences. So this is the essence of what I'm trying to talk about today. And I will start by saying that the biggest impact on sustainability is being made by very small molecules, some of the smallest molecules known in chemistry. That's hydrogen, carbon dioxide, and water. And our objective, at least one of the objectives in sustainability, is to be able to access clean fuels, clean air, and clean water. So this is what I want to discuss today. Hydrogen burns with no byproducts aside from water. So it's a very clean burning fuel. Carbon dioxide could be extracted from air potentially and converted into a clean fuel as well, thereby cleaning the air. And water, especially today, I want to talk not just about purifying water, but about extracting clean water from air to provide it as for drinking, as a drinking water. Whatever solution we come up with in materials that would integrate into a device, it's going to be complex. Look at the iPhone. The iPhone or the cell phone has more elements than the human body. So we need to be able to understand how complex materials operate. Fortunately, I think this is the blessing for humanity, is that we have the periodic table, and it's the chemists have figured out how to use the periodic table to solve problems. Without it and without chemists, it's very difficult to address these sticky problems that I mentioned: clean energy, clean air, clean water. So chemists have done very well taking atoms and combining them into molecules. Okay, and in our chemistry, we have then extended this to taking molecules and linking them to make frameworks. The reason these frameworks are exciting is because they encompass space within which one can control matter or store or separate those small molecules that are so responsible for the achieving a sustainable future. So let me just say that if the molecule to the atom is what the framework is to the molecule, let me explain what I mean by that, is that the molecule puts the atom in specific geometry and connectivity. That's really what chemists have been doing for the last 100 years, is making discrete molecules and controlling the connectivity and geometry. And to achieve a sustainable future, not only do we need these molecules, but we want to use these molecules as building blocks to put together materials that are capable of seeking out those small molecules those small molecules like hydrogen and CO2 and water from the atmosphere. In our exercise of putting these molecules together, we need to pay special attention to what I call the linkage. The linkage is the points at which these molecules come together. Once you control this linkage, you can control a lot. You can control the stability of the material, the geometry overall of the material, and many other things, as you will see shortly. So from a chemist's point of view, the framework extends what we know about the atom and the molecule into extended structures, into 2D and 3D. But let's ask very difficult questions that would address these difficult challenges. How do we make every atom in a substance a surface? If I can make every atom in a framework a surface, then I could use that atom as a site onto which to put a molecule like hydrogen or CO2, to extract it from air and use that atom that I have exposed as a surface as a parking spot, let's say, for those molecules. So this is really what we're trying to do here, and what we have been doing in reticular chemistry, where you take an object and then open it up, okay, where every component of that object becomes a surface. That's why we talk about ultra-high porosity, so that every atom can be accessed by an incoming molecule, incoming gas molecule. So then this leads me to the chemistry that has led to this exposing every atom and making every atom as a surface in a substance. And that's reticular chemistry. And I define it as the chemistry of linking molecular building blocks by strong bonds to make crystalline extended structures. Molecular building blocks so that we can design structures in a rational way. Strong bonds is to make materials that are thermally and chemically stable and can stay, let's say, in a power plant, working in extracting CO2 from flue gas for a long time, for years, before it would have to be regenerated, and crystalline so that we can have materials that have homogeneous structures, but also we can characterize them on the atomic level by single crystal X-ray diffraction. All these three things have been a challenging chemistry, and let's say reticular chemistry has solved these issues. And so we are ready to take these materials and use them to address the sustainability challenges. The result of reticular chemistry has been metal organic frameworks. And they're composed of metal oxide units that are linked by organics to make extended structures. And back in '95, we showed how these could be crystallized from strong bonds. In '98, we showed how their structures could be made porous and they're architecturally robust. And in '99, we showed that they have the highest surface areas ever achieved in a material. Not only once you have control over molecules and how they come together in different linkages, your linkage here is metal oxide. In covalent organic frameworks, the linkages are organic. And so we first reported the first extended organic structures in crystalline form in 2D in 2005 and in 3D in 2007, created a whole new area of materials. And then recently we showed how one can do molecular weaving. I won't talk about this, but this is another aspect of sustainability, is to create materials that are not disposable, that can be resilient and can stay operating for a long time. So this is how a MOF is made. It's a solution. You take a solution of an organic acid with a solution of metal ion under these conditions to make an extended structure. Okay, this looks simple, but it took us a while to figure out the conditions under which to crystallize these. And that's really opened up the whole field of MOFs. This is MOF 5, and you can see here, using gas sorption isotherm, one can derive the pore volume, which is 61% of those crystals is open space. And that corresponds to a surface area of almost 3,000 meters square per gram. That's basically, in 1 gram of material, you have the surface area of an entire football field. And that's the space onto which you can then stack hydrogen or carbon dioxide or water in terms of achieving the clean energy, clean air, and clean water objectives. But I would just want to advance the idea and show you that in MOF 5, we have achieved this vision of exposing every single metal atom by having these metal oxide linkages linked by organics. And the reason MOF 5 and other MOFs are architecturally robust is that you can see many 90-degree interactions where your linkers are turned 90 degrees to each other, just like, let's say, struts in a building. When you're making a building, you're trying to maximize the number of 90-degree interactions, whether they are the adjacent 90 degrees like this or turning one rod with respect to another. That makes a very stable architecture. That's why MOF 5 is an incredibly architecturally stable material. But in so doing, you have exposed the interior of your crystals. Your crystal's interior is riddled with openings, such as what you see here. And to prove that, we have shown, I will show that shortly, but before I get there, I just want to say that once you know the conditions under which to make this linkage, then you could employ a linker that has different functionality and therefore functionalize and craft the pores. This becomes important later when we do CO2 capture, as well as by using longer linkers, you can make larger pores so that you can incorporate progressively larger and larger molecules. So the fact that MOF 5 is architecturally robust means that we can take that crystal of MOF 5 and cool it down to 30 Kelvin and look at where the gas molecules are residing in the structure. Find out, indeed, if our vision of every atom being a surface is realized. And so that's the experiment that we did. Take that crystal, cool it down to 30 Kelvin. Fortunately, the crystals don't crack. They don't lose their crystallinity. And here's the first time ever that someone could find the crystal structure of a large pore material without anything in the pore. And you can see that as you introduce argon or nitrogen, you see that they are sticking, or the adsorptive sites lie on the metal oxide unit. But not only that, we find that indeed that there are many sites on the metal oxide units. And as you can see here in the yellow balls, that's where argon or nitrogen is binding. These are all binding sites onto the metal oxide unit, as well as we find that there are adsorptive sites on the 6-membered rings of the organic, as well as the edges. So indeed, everything you look at in structure, every atom, every face of the polyhedron linking these structures together is an adsorptive site. And Thus, we have really the exciting thing in reticular chemistry is that we have successfully realized didn't successfully realize this movie, but anyway, that every atom that you're looking at in a MOF structure is an adsorptive site. That's why they have incredibly high surface areas. This structure here of MOF 200 has a surface area of 6,400 meters square per gram. That's almost 2 football fields for each gram of material. So that the exciting thing is that not only can you use that metal oxide linkage that I showed you, but you can use many different metal oxide linkages, and not just zinc, but also elements from or metals from the entire periodic table. So different metals in these SBUs, and then one can use organic linkers that are very simple and natural, like this lactic acid or citric acid, and these widely available linkages as you see here. But also, if you're ambitious and you want to bind enzymes, you could use very long linkers such as this one. So many different linkers of many different composition and geometry have been used, and you can see here that we go for thinner linkers so that to make progressively higher and higher surface areas. But the idea is that there is a variety out there that allow you to have a vast number of materials, depending on what kind of application you are looking for. So I won't go through what we have done in covalent organic frameworks, but just show you the latest results on one covalent organic framework. Now, these contain no metals. The backbone is entirely organic, and you can see here that this structure made entirely of carbon-carbon linkages or olefin linkages, and that this can be crystallized and made. And this shows the X-ray powder diffraction with very sharp lines for the structure. But more importantly is that we find that this structure is extremely stable in strong acid, strong base. You see the X-ray powder diffraction, the crystallinity is maintained, the structure is maintained. We check that from X-ray powder diffraction as well as by IR. And you see here even corrosive materials like butyllithium does not affect this material. And that's what you would expect from a carbon-carbon bonded backbone and a carbon to nitrogen double bonded backbone. That backbone that I showed you here, that I showed in this slide, if you would like to introduce metals for catalysis or for other purposes, you can always hook those up covalently to the backbone. But this shows that, in fact, the impossible dream of building structures that are crystalline and ordered using very strong bond is realized. And such a structure, as I showed you with the stability measurements, could remain, let's say, in a power plant for many, many years, extracting CO2 from flue gas. So that's the vision there. And I just want to say that furthermore, we can characterize these by single crystal X-ray diffraction, is that we developed in a collaborative project with Wei Wang group in Lanzhou University. We developed methods using modulators like aniline to produce single crystals of COFs. These are crystals that molecular chemists are used to making. Now we are making them for extended structures that are linked by strong bonds. This is really a dream come true for chemists, and it allows us to characterize COFs with the same accuracy as you would characterize molecules. So what we have then is really a worldwide activity in MOFs and COFs. And as Dr. Othman mentioned, this is practiced now in over 100 countries around the world. Why? Because reticular chemistry allows you to make materials that where the principle is, if you can think it, you can make it. That's rare. in chemistry. So if you can think a structure, the likelihood of making it is extremely high. That's what the excitement is all about in this field. And so if you just look at what these materials and the way we make them allows us to do in terms of sustainability and in terms of making devices, let's just look here on the left. We use nature's building blocks, minerals and organics, to make a vast number of compositions and material, almost infinite number, okay, that you can make, that you can choose from. They're crystalline, so they have well-defined structures, homogeneous pores, and therefore they have reproducible action, reproducible operation. They have ultra-high porosity, and their pores have no walls. That gives you very high capacity for storage of those gases and fast kinetics. So fast kinetics for uptake and release of those gases so that the cycling is fast. You don't have to wait too long to take up, let's say, hydrogen or CO2 and take it out. So that, again, that impacts on the throughput of the system. Design of the pore environment is that if you can craft the interior of these materials so that you can have cooperative phenomena like oxygen binding, let's say, to hemoglobin. The same kind of phenomena is observed in the water harvesting systems. And I'll show that shortly. Strong bonds, I've already mentioned, that gives you the thermal and chemical robustness that you need for repeated cycling. So for hydrogen storage, the idea is to make systems, let's say a MOF, as you see here in red, that can take up oxygen, in this case, hydrogen, and the hydrogen is interacting with the framework. And its interaction with the framework allows you to pack the hydrogen molecules closer to each other, much closer than they would be without the MOF. In this case, you see that the hydrogen molecules are aggregating around the framework, and we use interpenetration to fill these pores with additional adsorptive sites. I will talk more about hydrogen in another conference I will mention shortly, but the idea with hydrogen storage is that you want the attraction of the hydrogen to the framework to be about 20-25 kilojoules per mole in terms of its binding energy. If you can obtain that, it would be then possible to make room temperature storage materials. But you see, the other requirements are things that we are already doing in MOF chemistry. And our initial results on hydrogen storage are exciting enough that Mercedes has used a pressurized tank using MOFs as a fueling source for this demonstration model, which is, I think it's quite exciting. So I just want to say that I don't want to say any more about hydrogen, but there will be a symposium held at KFUPM and organized by Professor Zain Yamani on the hydrogen economy status and ambition on Wednesday, March 30th of this next month. So I will speak at that and give more details as to the requirements for hydrogen storage and the state of the art and where we are in our own research. Now I want to move to CO2. And just this chemical equation tells you how much, let's say, every tank of petroleum ends up producing in terms of carbon dioxide. So every tank of let's say a small size sedan is producing almost 81 kilogram of CO2. So you can imagine that there's just so much CO2 in the air, almost double the amount before that was there before the Industrial Revolution. So the problem of CO2 capture is divided into roughly, one can divide into two domains. One domain is extracting CO2 from air, where it's very dilute, but it exists at 400 ppm. Okay, so it's enough to cause all the damage to the environment. The other challenge is to be able to capture the CO2 from point sources such as power plants. And there the concentration is much higher than in the air. It's 5 to 16% of CO2, depending on whether you're burning natural gas or petroleum. So these two challenges, capturing CO2 from point sources and capturing CO2 from air, require slightly different functionalization of the MOF. So let me show you what then we need to be able to do. The minimum requirement for a material to be a good CO2 capture material is that first you need high capacity, so that when you're cycling, you're not doing so many cycles to achieve the desired CO2 capture. You need materials that are water stable, okay, because there is water in the atmosphere, there is water in flue gas, and you need a material that is not going to oxidize because there is oxygen present in all these binding events, and you need the material to be cyclable. You also need to be able to say that your regeneration temperature is not very high, because that's your energy input, and that's basically the binding energy of CO2 into the pores. So you don't want that to be too strong that you have to heat the material up to hundreds of degrees to remove the CO2. So all of these are extremely challenging, but you can see from my earlier description of MOFs that we've been working for the last 25 years to be able to make materials that meet these requirements. So I don't expect you to read this table, but this is what's available out there in terms of materials for addressing the CO2 capture. And sadly, I can say that there isn't an ideal material. You can see the challenges here for each class of materials. So it's just a question of how we can improve these materials. And if you can improve them in an incremental fashion, there would be many power plants that would deploy these materials. So I would say that this is an ongoing challenge. In terms of stability of the materials, in terms of capacity, those are two very outstanding, let's say, challenges at this point. So our approach has been to take MOFs and functionalize the MOFs. In this study, we have been functionalizing them with amino acids. The amino acid has a carboxylate on one end that hooks up to the zirconium in the structure in a strong bonds, so that doesn't come off. And the amine group is selective to extracting CO2. So, so this is what we are able to do. This particular structure we call MOF 808. You can see these units that have the green ending is basically glycine, and you can see that the structure is replete with glycine units. Each glycine unit potentially can bind a CO2 molecule. And this is where every atom in a structure is an adsorptive site, and the structure is open, sufficiently open to allow CO2 in and out with great ease. Now, what we find is that as you are binding CO2 from humid in the presence of water, you make this bicarbonate ion pair. And this is operational when you have a lot of CO2. So let's say if I'm binding CO2 from flue gas, this is what I'm going to make. I'm going to make this unit. And notice that bicarbonate is part of what you make. And this is a very unstable molecule and does not require any heating to remove the CO2. You can just pull vacuum on this system, as we have shown in this recent paper, to remove the CO2. So that's the kind of control that one can have inside the pores. Now, in systems where, like for example, extracting CO2 from air, this is the mechanism that would be operational. in that now you have to make carbamate or carbamic acid, depending on the pH, and that requires heating, some heating, 40 degrees to 90 degrees, depending on the system, to remove the CO2. What I'm trying to say here is that as CO2 penetrates through the pore, there are different chemistries that take place depending on whether the CO2 is coming in high concentration from flue gas or is coming in low concentration from air. And accordingly, the chemistry in the pore can be adjusted. Okay, so we took this system and scaled it up to a kilogram to make this CO2 harvester. And you can see here that this is basically the sorbent is placed in two compartments so that one can do the adsorption while the other is doing desorption. And here you see that this is simulated air. This is exactly the amount of CO2 in air right now. And you can see that we can cleanse that air from CO2 and reduce it down to less than 0.02 millibar from 0.4 millibar. That's 400 ppm down to 20 or so ppm. With flue gas, this is what flue gas, let's say coming from burning petroleum, 15% CO2 under these conditions, you can cleanse that flue gas down to 2% CO2. What I'm trying to say here is that it's possible. It's possible to design materials that can extract CO2 from air, that can extract CO2 from flue gas. And now what we need to work on is the long-term stability, let's say, of these materials. This is a problem that is universal in the CO2 capture world, but I showed you coughs, and coughs have a very robust backbone, and this is definitely materials that we are investigating to overcome the long-term cycling stability of these carbon capture systems. Okay, so I would like to now turn to water, and I need not tell this audience the water stress in the world. Almost 1/3 of the world population lives in water-stressed regions. And even the watered regions of the world, there are always questions about water purity. And third is that 160 countries around the world import their water. They rely on another country for their water. So this is a major problem facing the world, and it's getting worse. So by the year 2040, it's anticipated that the water stress will get even worse because we are using the underground water a lot faster than it's being replenished. So you can see here in the US, even the areas that you think are highly watered are expected to become water stressed because of overuse of underground water. And of course, the other areas of the world where there's less rain, this climate change is aggravating this problem, making it much worse. So from my point of view, there is potentially a solution out there. There's a lot of water in the atmosphere, almost 13,000 cubic kilometers of water are in the air at any one time. So if we can harness that water, then we would have tapped into a recyclable resource and therefore deliver water to areas that require it. Now, there are many things that you see on the internet that promise that they do extract water from air. That's true, but that's a humid air because they work on direct cooling of air. So these systems, no matter what they claim, they only work at high humidity. So they don't work at humidity levels of less than 60, definitely not the normal humidity levels that you find in the desert, especially in the Mediterranean region and around the Mediterranean region. So our idea is that if we could create or design a material that works in the red regions at low humidity, it should be possible also to deploy such a material in the more humidified region where there is water, but the water may not be clean. So my vision is, could we harvest water from air anywhere in the world at any time of the year? And again, the idea here is that could we use reticular chemistry to design a material that works at very low humidity? And if we do that, then we would have achieved this vision. So why is it that these machines that are advertised on the internet don't work? And why direct cooling is a problem? Here's the psychrometric chart. It's a plot of the water vapor in air versus temperature. And these are the humidity lines, okay? And I've colored the humidified region in green and the desert regions in pink or brown, light brown. But you see here that if I'm in a city that is where the temperature is 30 degrees C and the humidity is 20%, if I was to extract water from that air, I have to cool down I have to cool down the air to 4 degrees Celsius to be able to extract the water. Now, if I have a MOF that is designed to extract water from air here, then I would concentrate the water into the pores of the MOF and therefore creating a more humidified environment. And therefore, if to get the water out, I would only need to reduce the temperature by 4 degrees in this example. So this blue line is not a viable method of extracting water from air. The red lines show you that you can turn desert air into tropical air by harvesting the water into a porous material. So again, there are many compounds, many materials that are being investigated for water harvesting. And if they don't meet one of these criteria, having high capacity, having fast kinetics, or work at low humidity, they are not going to address the water stress in the way I have been describing. So our first discovery of water harvesting in MOFs came while we were studying CO2 capture. And as I said before, when you're studying CO2 capture, you're also having to separate CO2 from water. So we were also studying water uptake into MOFs, and this is the MOF zirconium fumarate, where we discovered that water is taken up at around 20% relative humidity, and it's taken up in this knee-shaped isotherm, which indicates a cooperative uptake of water. The amazing thing is not just that it has this cooperative knee form shape of isotherm, but that we can take the water out at 45 degrees C. And so immediately my thinking was that you could take this to the desert, extract water from air at night, and during the day when it heats up, you can take the water out and condense it. And that's basically the vision that we wanted to realize. But as you cycle, we noticed that after a slight drop in capacity, before it stabilizes and the material behaves very normally, where you have taking up water and releasing the water repeatedly. We wanted to look into why was there a slight drop here, okay? And it turns out that when you do single crystal X-ray diffraction and neutron diffraction, you find that water molecules, the very, very first water molecules bind to the metal oxide units through hydrogen bonds to the OH units that are part of the clusters. And the water molecules cluster, in this case, tetrahedral and cubic forms. And it is these water molecules that are hydrogen bonded to the metal oxide units that act as seeds onto which other water molecules are brought from the air. And the drop that we see in the previous slide is due to these water molecules sticking so tightly into the pores. So these are not the water molecules that we actually take out. So they stay there and they act as seeds, extracting more water from the atmosphere. So we designed a prototype to show that this works in the desert. This is a prototype with a box that is a box within a box. And the moth is in this smaller box. Desert air, water from desert air goes into the moth. And then during the day, you close the outside box. The inside heats up as you expose to sunlight. Water comes out and condenses on the walls of the box, and you can collect water. So we took this into the desert. This is what it looks like, a plexiglass box within another box. And we took it to the Arizona desert, and we were able to harvest 200 milliliters to 300 milliliters for that kilogram of moth. Now, it's not a lot of water, but certainly it proves the point that you can extract water from humidities as low as 20%. The water is pure. It's distilled water. There's absolutely no metals or organics into the water. So
action.
The student volunteered to drink the water. So it's pure water. The strong bonds that hold the backbone of the moth together allows you to have a stable structure in water and no leaching of organics or metals. So that's a zirconium structure. And the nice thing about reticular chemistry is that you can go from potentially a material that is expensive like zirconium into a material that would be a lot cheaper with aluminum. So aluminum is cheap, and it could be, you can use it to make this moth. This is an amazing moth we call moth 303. It's made from aluminum rod oxide SBUs and this linker, which you can buy. And the structure takes up water at very low humidities. I'll show you the isotherm in a second. But the amazing thing about this structure is that if you are a molecule floating inside the pores, this is what you will see. You will see hydrophilic regions and hydrophobic regions. And I'm going to color them. This is the hydrophilic regions, and these are the hydrophobic regions. So if I'm a water molecule, I first go to the hydrophilic regions, and then I'm bound by hydrogen bonds to the framework. And then the structure is building up across the hydrophobic region to the other hydrophilic regions. So you have water growing inside the structure, and the balance between the hydrophilic and the hydrophobic region allows you to also adjust how tightly water is bound into the framework. Okay, so let me, I see that the time is creeping up. Let me just go through the last two or so slides showing another prototype. In this prototype, based on moth 303, we took it to the Mojave Desert. And you can see here in the Mojave Desert, the relative humidity during the day and night. And during the day, it goes down to about 7% relative humidity, and the moth is still taking up water. Okay, so this basically realizes my dream of harvesting water anywhere at any time of the year, because this moth is capable of taking up water at very low humidity. This is a picture showing the water dripping into the, okay, it's probably not going to work. Okay, there was supposed to be water dripping into the, okay, there it is. That's real-time harvesting of water in the Mojave Desert. So we collected 1 liter of water per kilogram of moth per day. And that's because we can push air through by a fan into the moth and do more than 1 cycle a day. So based on this fast cycles, you can remove the water within minutes. You can design another prototype that delivers 4 to 5 liters a day. But that's based on only 200 grams of water, 200 grams of moth. This is 200 grams of moth 303 gives you 4 to 5 liters of water. And so based on those results, it means that the moth works everywhere in the world at any time of the year. And even in the Atacama Desert, which is one of the driest deserts in the world, at driest time of the year, you can still get some water out of the air. And this I plot for many parts of the world, including Riyadh and many of the Mediterranean regions. And you can see that up to almost 90 liters of water could be harvested per kilogram of MOF per day. The nice thing is that the MOF stays in the device for many, many years, for 5 to 6 years. For the lifetime of the, at the end of this journey, if the MOF is not performing well, you can take it and separate the components by using strong acid and recombine them in water to make the same material. So it's completely recyclable with zero waste. And this pertains to the subject of this conference, which is the sustainability. So using X-ray diffraction, we have figured out the position of each one of the water molecules into MOF-CO3. And this is a movie that will show one pore. We're going to cleave the pore in half to show where the water molecules are going. They first enter into the hydrophilic regions. That's it. And now you start building up the structure of water in the hydrophobic regions. So you see that water molecules are bound to each other beyond just the framework to fill the pores with water. Each position that you see here in red has been determined by single crystal X-ray diffraction. Okay, so before somebody in the audience tells me that we're drying the air, let me just say that if we give each person on our planet 50 liters a day of water, we would have only used less than 0.002% of the water that is in the atmosphere. So there's plenty of water in the atmosphere. The exciting thing is that we're creating distributed water, mobile water that you can personalize. It's pure, can be made to be drinkable by mineralizing it, or it could be used for agricultural purposes. And my dream is that once this is fully commercialized, that we would achieve water independence. And we are no longer dependent on the grid. We are in control of our own water. This is part of a much larger picture that I wanted to just talk about in this last slide, is that now we have the materials to take water out of the air and create fresh water, and take CO2 out of the air. And then I didn't discuss the conversion of CO2 to fuels. That's an aspect that my colleague Peidong Yang will later talk about in this symposium. But we're looking at what I call the air economy. This was published with Peidong and Dr. Clark recently. Our vision of creating an air economy which is based on getting clean air, clean energy, and clean water by just using sunlight. So that's the end of my talk. I want to acknowledge my students in addition to those that I acknowledged during my presentation, and acknowledge the support and collaboration of these partners, as well as thanking you for the invitation. And I'm delighted to answer any questions that you may have.
Thank you very much, Professor Omar, for this enlightening talk about how we can utilize the chemistry of reticular chemistry and building materials to our end use. So in questions, I would like to see, we have Mr. Yahya Al-Janabi. In your opinion, in our region, what is more relevant? To do research on developing new types of materials, or to find applications and use of materials already discovered?
I would say that as a scientist, I think you have to pick a project, an idea that you're interested in, and take it where the science goes. Okay, and so I have shown you, I never dreamt that we would be designing devices. I don't know anything about designing devices, but we happen to design a material that takes up water from air. We weren't just going to sit there and look at it in the lab. We wanted to take it to the desert and show that it works. And so the human innovation and the human mind is an amazing thing. And we all have colleagues that can help us in getting to that next step. through collaborations. So I do completely agree with the introductory remarks of Dr. Al-Saggaf when he said that there are no boundaries. And so we need to be really intellectually flexible and not to put walls between everything. So this story of going from basic science, of making strong bonds in crystals, all the way to a device that shows that you can extract water from air, didn't happen overnight, okay? But it required hard work that takes you from what you're comfortable with into an area where you're not familiar. But we learn, right? We learn how to do. People like me can learn engineering, okay? We're not just chemists, so we can extend our contribution beyond. And actually, it's a matter of survival for scientists nowadays to be able to cross disciplines. I think if you're an emerging scholar and you can't cross disciplines, then you will not be able to advance. So,
thank you.
Yeah, I hope that answers the question.
Another question from Dr. Faiz Rahman. Please inform about the economics of water from MOF. What could be impact, especially at low humidity levels?
Well, the material is made of aluminum, and I showed you that you're only using 200 grams of the MOF to deliver 4 to 5 liters of water a day. That would be sort of in your kitchen for drinking water. And that will operate for 5 years before you have to replenish and recycle the MOF. So to me, that's not the question. The question is, have you solved a problem? And then the economics of it, if you solve a real problem that people really are looking to solve, the economics will fall in place, okay? So the economics depends on many things, including societal demand and business models and all these other things that go with realizing an invention in terms of applying it to commercialization. So I don't want to say that the thing is cheap, but I also don't want to say that the thing is expensive, because clearly the fact that this MOF is designed to extract water from low humidity air where there's no other material that can do it in an energy efficient way tells me, and you're using only 200 grams of it, what's the rest of the cost? It's off the shelf parts of that instrument. So
thank you.
It's about solving a problem yeah.
There's another question from Dr. Naveed Malik. What could be the impact of various pollutants? So let us say MOFs are made from metals with organic linkers. Do we expect any leakage or leach of these materials in the drinking water?
No, I showed that these materials are robust, and we tested the water, all the water that we harvest, we test, and it falls way below the allowable amounts of metals, organics, and whatsoever. We detect no metals, no organics. And the reason is not just a strong bond, but also, let's say in the water harvesting system, the first water molecules, they basically sit there and they stay there the entire time you're doing the uptake and release, because you're not taking those out. Those become an integral part of the structure, protecting any hydrolysis that may take place between the aluminum and the carboxylate. That's the beauty of having figured out where the water molecules are going into the structure and understanding which water molecules that you're drinking and which ones that are staying in the pores, seeding the uptake of water from the atmosphere.
Okay, thank you. Another question from, let me see, from an anonymous attendee. Do you think we will ever see intrinsically conductive MOFs or MOFs with even superconductive properties one day?
Well, of course, the answer to that is yes. I do foresee that. We're already making conductive MOFs. There are many reports already in the literature on conductive MOFs. But once we as chemists know how to control matter on the atomic and molecular level, the possibilities are absolutely limitless. So, I would say yes, only because we already have done things that everybody said that can't be done. Almost every milestone that I've shared with you today, whether it is the strong bonds getting to crystalline structures or whether making coughs altogether, people said it's impossible. In fact, people wrote articles about justifying why it is an impossible goal. So I would say yes.
Okay, another question. You see, we have a lot of questions, so we will go by them. What about the using of nanoparticles in MOFs? This is a question by Mr. Aida Azzam. Do you think it will be better than using other linkers or modifying on the surface of MOFs?
Well, I think it just depends on the application. We've used nanoparticles, let's say of metal nanoparticles, and enclose them into a MOF. And then you can see better activity because of the interaction of the nanoparticle to the framework, and also because access to the nanoparticle is controlled by the pore size of the MOF. So it depends. In catalysis, I would say that's a very interesting approach. But for water harvesting, it's not, because then your nanoparticles will leach, but also water harvesting system have to be absolutely crystalline so that those water molecules sit in their thrones, in their chairs, exactly in the locations where you want them. Any kind of disorder in the structure, amorphization of the structure, will result in an undesirable water uptake behavior and lowering of the working capacity. So it's an example of where crystallinity is absolutely necessary for obtaining a fully functional system for extreme conditions.
Thank you, Dr. Omar. Let us say another question from Mr. Fawaz. Did you address any health concerns from harvesting water from air? Was this covered on your research?
Health concerns by harvesting water from air. Yeah, it hydrates people. That's not a health concern. There are no health concerns. I mean, what could that be? We tested the water, it's pure. So I'm not sure what is really at the heart of this question. Is this one of those issues where you say you're
I think that he's looking for... Is this
about dust or contamination from the air, or?
Maybe.
Well, the MOF itself is a filter. It only allows water in. If you have large organic molecules, or they will not fit in the pore. So it's a natural filter. We have run some of these devices in the middle of the fire season about 2 years ago. There's absolutely no impact on the performance of the MOF. At the end of the day, if you are in a dusty atmosphere, you can always have an air filter similar to the one that you would use, let's say, in a car, that could be put in the device to make sure that dust particles don't get in and complicate the working of the device. But we have not observed any contamination in the water or any. I mean, if it has no contamination, then there is no health concerns.
Okay, I think one final question is due. How do you see the cost of these new type of MOFs and COFs compared to already existing technologies that have been utilized for years and years? And if we are looking at the natural gas industry, they are working with zeolites, like that. Can you give us an insight on this?
There are MOFs that are about $2 a kilo, and there are MOFs that are $100 a kilo. There are MOFs that are $10,000 a kilo. It depends. You have 100,000 MOFs known and about 500 COFs known, and you have a chemistry that produces infinite number of materials, infinite number of building blocks, and different metals. So it just depends. It depends on your application, it depends on the material, it depends on many things. There's no general statement that I can make concerning cost unless we know what is the application and what value will the MOF bring to the table. If it brings a value, like our cell phone, for example, going from a wired phone into a wireless phone, you pay $1,000 for this. While the wired phone you can buy for $10. So it brings value. To extract water from air, you're bringing value, you're harnessing a new resource. You have to think, you have to put that into your equation. So the answer is that there are some cheap MOFs, dirt cheap MOFs, and there are some expensive MOFs, depending on the components and the application.
Thank you, Dr. Omar, for this informative talk and a very great talk about how we can utilize reticular chemistry in different applications of life and how to sustain life by using these structures. Thank you again very much. It was an honor to hear your talk.
Thank you so much.
Now we would like to go to Professor Gogotsi. I hope he's here. Professor Yury?
Yes, I apologize. I had problems to connect, but I think I'm finally in after multiple attempts. And I missed Omar's talk. My apologies. Had another meeting as well. But right. I'm here and should be able to present momentarily.
All right. Thank you very much. Thank you very much for joining us. So let me introduce Professor Yury Gogotsi. He's a distinguished university professor and Bach professor of material science and engineering at Drexel University, Philadelphia. Professor Yury is a distinguished professor and Charles T. and Ruth M. Bach Professor of Material Science and Engineering at Drexel University. He also serves as director of AG Drexel Nanomaterials Institute. His research group works on 2D carbides, nanostructured carbons, and other nanomaterials for energy, water, and biomedical applications. He is recognized as a highly cited researcher in material science and chemistry. He has received numerous awards for his research, including MRS Medal, ACS Award in Chemistry of Materials, Materials Today Innovation Award, Gamma Prize, European Carbon Association Award, and S. Sumaya Award for IUMRS. He has been elected as a fellow for the American Association for Advancement of Science, Materials Research Society. He is also a fellow of American Chemical Society, the Electrochemical Society, Royal Society of Chemistry, International Society of Electrochemistry, as well as the World Academy of Ceramics and the European Academy of Sciences. He holds multiple honoraries doctorates from several European universities. Welcome you again, Professor. And today, Professor Yury will talk to us about two-dimensional carbides and nitrides for an open path to future energy technologies. Thank you, and please welcome.
Well, yeah, thank you very much for the invitation. Thank you very much for this kind introduction. And while I was a few minutes late, I'm sure there were many questions to presentation of Professor Yaghi, who developed an entire field of metal organic framework materials. And I'm going to talk about a family of materials which has something in common with MOFs, because it's also a very large potentially family of materials. Designer materials with really infinite number of compositions possible, but those are two-dimensional materials. Carbides and nitrides of transition metals, which we called MXenes, where M stand for a transition metal, X stand for carbon and nitrogen. And in these schematics, you can see on the cover slide, red dots are M atoms, and small black dots connecting them are carbons, nitrogens, then come in a variety of structures, and
Doctor,
of course offer a variety
Dr. Yury,
of. Yes.
Can you share your presentation? Or?
So you cannot see my presentation now. My apologies. Let me see what's going on.
Go to share content.
Because yes, I did. I thought I was sharing the screen. Can you see it now?
Yes, now we can see it.
Okay, terrific. Sorry. Again, something went wrong here, but now you can see it, and I hope it's a full screen format.
Just use slideshow, swap displays, because.
Okay, one more thing to deal with. Now I need to get my mouse on the right page. Swapping the slides. And now we should be finally where we should be, right? Yeah.
Yeah, but make it a little bit smaller. Okay. All right.
Okay. Is it good like this now?
Yeah, please.
Okay.
Excellent.
Wonderful. Okay. So once again, then those are MXenes materials which offer us a variety of carbide and nitride structures here. Let me just go in a few more details here. So those are M atoms in the structures which are few nanometer, few actually atomic layers in sub-nanometer, with again black dots, carbon and nitrogens here. What is unusual about those materials? Majority of them are actually metallic materials with a high density of states at the Fermi level, high concentration of carriers. They have conducting carbide and nitride core. But their surface looks like a surface of transition metal, oxide, hydroxide, chalcogenides, halogenide, depending on what surface termination you have here. So they combine properties of metals and non-metals here. And this is by itself is quite unusual, quite uncommon here. But they come in many different structures. We distinguish them by the number of layers, like a 2 layers of carbides and nitrides, and for example, like a 1 layer of carbon nitrogen. You can have simple structures. You can make solid solution on M side and solid solution on X side here. And the first one was titanium-32. It is still the most studied material, and it was published in 2011. Michael Naguib was a PhD student working with Professor Michel Barzo, myself, and he made the first MXene here. By now, we have more than 30 stoichiometric MXenes produced, more than 20 solid solutions published, which include atoms of transition metals marked here in blue, carbon, nitrogen, surface termination can be oxygen, OH, chalcogens, halogens, and then come in multiple structures. If you just multiply by the number of atoms, by the number of structures, carbon, nitrogen, you end up with more than 100 of stoichiometric compositions. Add 10 different surface termination demonstrated so far, you end up with at least 1,000 of materials with a defined composition. And if you consider solid solutions, it's really become an infinite number of materials. So how do we make those materials? Initially, we started with so-known max phases, layered ceramics, which contain carbide nitrides layers interleaved with metallic layers like aluminum, or it can be actually layered carbides with, say, aluminum carbide, or 2 layers of aluminum, silicon as elements connected. Those are strongly bonded ceramic materials. So we cannot eliminate those materials by simply sharing. So what we do, we etch them selectively, remove, say, a layer of aluminum, or one of other elements marked here in blue. And we end up with layers of carbides and nitrides now, terminated by atoms coming from the environment. It can be oxygen, OH, chlorine, depending on what we use for H, emulsion salt, aqueous salts here. And now they look not like a ceramic, but more like a thermally expanded graphite. And then weak bonds between those layers can be easily broken by intercalation, syndication, forming single layer flakes of MXene. Research in MXene started just a little bit more than a decade ago. First paper, as I mentioned, was published in 2011. Last year, about 2,500 papers, according to Web of Science, were published on MXenes, and people from more than 2,600 organizations published on the topic. So it's really growing field here. So what do we have today? We can make structures, as I mentioned earlier, with 2, 3, 4, and even 5 layers of transition metal. It's actually by itself quite unusual, because those are very well-defined structure, just like a molybdisulfide. There will be always such number of layers, but they're much more rigid. So they're not flimsy, unlike, say, graphene layers or other thinner, softer 2D materials. Here. We can also make atomic sandwiches with one transition metal, for example, moly being on the surface, another one, for example, titanium in the middle. It's also possible to make in-plane ordered structure with alternating atomic columns of different elements, as it's shown here. And it's also possible to make materials with ordered vacancies, like a missing atomic columns on the surface here. And we can also mix and match in different amounts atoms in the M layer or X layers, opening tremendous number of opportunities for designing two-dimensional materials with a variety, very large variety of structures here. So what we have with this is very large material space to be designed, developed, explored. So we start with the ceramic materials like MXphase, etched, for example, in acidic etchants here, and we produce a number of materials, including single flake materials here. What is also important? It's a scalable process. We can make hundreds of grams of materials in our laboratory, kilogram reactors are in industry, but potentially we take ceramic, we put it in a container, we etch it. So it means that the process is scalable to almost probably infinite volumes here. And right after etching, actually, we can take a slurry of materials and, for example, by Dr. blading, make a film which has strength compared to aluminum foil, high conductivity, for example, this one, 15,000 Siemens per centimeter, and process it in electrodes for batteries, supercapacitors, membranes for water desalination, filtration, gas separation, and many, many other applications there. So this is just a 1 micron film. It is supported in this case, but starting from about 3 microns, it's possible to make freestanding film which can be handled and processed without support here. Why can we work with these materials using aqueous dispersion? What is very, very important for actually sustainable processing and manufacturing here, because there is a high negative charge on the surface. Zeta potential of MXene typically ranges between -30 and -80 millivolt at pH close to neutral, allowing us to very easily disperse these particles in colloidal solutions. And starting with the ceramics, we end up with this etched material, disperse it in water, and we get this colloid of two-dimensional particles. If we have a colloidal solution in water, we can use any known processing technique to produce films, produce patterns. We can do 2D printing, 3D printing, spin coating, spray coating, deep coating, you name it here. What is important, we don't need any surfactant, unlike, say, for graphene, carbon nanotubes, metal nanowires, nanoparticles, or binders. Dispersion will happen because of high negative charge on the surface. And after that, also this functional groups help MXene particle to stick to each other strongly here. So it's a great, of course, to have a huge family of materials which potentially can include infinite number of compositions if solid solutions are considered. But we already have many different materials. So it's always important to think what can this material bring to the table? What are properties they bring? And one of them is they really, among them, there are many that are really good metallic conductors. So we have two-dimensional water-soluble metals like metallic clays that can be produced in this type of flake. So it's about 20 micron flakes in optical micrograph of titanium carbide MXene. These flakes can be assembled into films. If you look at single flake at high magnification, you will see that those are single crystal particles. They electron diffraction shows their crystalline nature. You can see some of them inherit this hexagonal shape from a precursor ceramic materials. You can also see it in optical images here, but they are conductive. They are water soluble. They also are mechanically strong. One cannot make, for example, 20 micron particles of moly disulfide in solution. It will break. Graphene oxide can handle it. And after those materials are basically the strongest material we know so far into the state here. But they also have, as you could see from the first slide, variety of colors because of tunable optical properties. Plasmon resonances, transverse surface plasmon being from UV to infrared range, offering also variety of optoelectronic properties. For example, for solar cells, light emitting diodes, and other applications here. They have many interesting electronic properties, which I won't have time to discuss today. Superconductivity has already been shown. A number of them are predicted to be semiconducting. I will focus on metallic MXenes today. Topological insulators, antiferromagnetic, ferromagnetic 2D materials have been predicted, but again, they are beyond the scope of our discussion today here. What is important and about these materials and the message I would like to leave you with before I move to energy-related applications of those materials here. Those are really tunable structure. We can tune the number of transition metal layers in the structure from 2 to 5 currently. We can use carbon, nitrogen, make carbides, nitrides. We have a dozen of transition metals to choose from. And we have surface termination. It's also possible to make bare, non-terminated structure, but of course they can only exist in high vacuum because transition metal will immediately capture oxygen and other molecules from air when exposed here. But we can move even further. We can graft organic molecules in the surface, for example, without killing electronic conductivity, because the electrons of transition metal in the, say, inner layer, particularly in thicker structure, will provide electronic conductivity. In assembled multi-layer structure, we can intercalate ions to further change the property. And for example, just by changing surface termination from oxygen to OH, we can change work function from 6 to about 2 electron volt. And in a similar way, all other properties, including, for example, plasmonic optical properties, others can be tuned. So again, this is where I mentioned there is some similarity to framework materials that you have heard about in the previous lecture of Professor Yaghi. Now, I hope by now you have some ideas of what those two-dimensional carbides and nitrides are. And I'm going to spend the rest of time talking about just one of the applications, the first one, and explored where a lot of work has already been done in storing electrical energy. If I really wanted to move into the world of sustainable economies. We need energy coming from renewable sources. We need to stop or minimize burning oil and gas and get renewable electrical energy from renewable sources, and we need to store it. Tremendous efforts are dedicated to this around the world. And everyone is trying to find pretty much high energy, high power storage solutions, as this Aragoni plot shows, where one can store as much energy, even more than in current lithium-ion batteries, do it faster, like in electrochemical capacitors. And this is, keep in mind, double logarithmic plot. So getting that point when we can have energy storage, which is fast, delivery is fast, is difficult. What do we need to achieve this? We certainly need to have storage in redox processes. Purely electrostatic capacitive storage will never store enough energy. We need charge transfer. So we need materials capable of redox processes. Also, if we want to have high rate energy storage, we cannot have bulk materials with solid state diffusion, which will always limit the process. Moreover, what does it mean, for example, taking your electric car to a charging station and charge it within 5 to 10 minutes, as Elon Musk promised us? It simply means running a high current through the battery. What happens if you run a high current through the battery? You produce Joule heating. If you use materials like in current battery, we have pretty low conductivity. So we need materials with high electronic conductivity. And of course, to move ions, which provide storage and transport of charges in batteries, we need ionic transport. And actually, MXenes answer all those demands here. They are metallically conducting, as I mentioned. They are actually 2-3 orders of magnitude more conducting compared to activated carbons, at least titanium, silicon, MXene, that are using double layer capacitors, which are considered to be like the fastest, highest power energy storage devices. They have galleries between the layers where ions can move. They also have transition metal on the surface, which can change oxidation state here. And this is something that may be invaluable in designing future energy storage systems. However, what we need to keep in mind, we cannot just take new materials, put them into conventional devices, and hope that miraculously they work better. It doesn't happen, because we need to understand now mechanism of charge transfer, transport of ions, formation of double layer and electrochemical reaction in the systems here. And I'm going to show you a few examples showing how different they can be from more conventional systems studied for a long time, like, for example, carbon materials from activated carbon to graphene or transition metal oxide. For example, if you look at water and solvated ions in water, aqueous basic ions between layers of MXene, and start bringing more and more ions, some ions will actually lead to electrostatic contraction between two negatively charged layers. When you bring cations, there is electrostatic contraction because of attraction between cation and the surfaces here. In some other cases, like potassium sulfate, there will be no change virtually in the spacing, good for, say, battery supercapacitor energy storage. Large changes, dimensional contraction or expansion, can be useful for electrochemical actuators as application. So we need to know dimensional changes. Then some ions can bring water in. Some ions can actually remove solvent like water from the layers. We need to understand this as well, what happens with MXene films. Now, even if you use aqueous solution and we try to develop aqueous batteries, we don't have organic toxic solvents which can work under even like an open environment, as long as no drying happening here, and which will be non-flammable. Ions will also behave differently. Some ions, lithium and sodium, will be partially desolvated and may show specific adsorption, electrosorption on the surface of MXene, leading to larger charge transfer. Some ions, like for example, cesium or magnesium, will stay solvated in between layers and won't come close to the surface. Naturally, what it means, ions that come close to surfaces, hybridizing orbitals with oxygens and transition metal, they will lead to stronger polarization, transfer more charge, and it means providing higher capacitance compared to some other ions, more charge storage. We also need to understand dynamics, because transport in a bulk solution is very different compared to transport in confinement. And we found that basically dynamics, diffusion coefficients of water molecules in presence of ions in confinement can be by 2-3 orders of magnitude lower compared to bulk materials. But if we know all this, how basically ions solvent molecules behave, we also need to understand whether we can really have fast redox storage. And the good thing, the answer is yes. First, we can have redox. You can see from X-ray absorption spectroscopy that oxidation state of titanium atoms in titanium carbide MXene in protic electrolyte like sulfuric acid. This is a typical electrolyte being used especially for fundamental studies, but also in your lead acid batteries in cars here. There is a change in redox state, so it means that we have charge transfer. We can store electrochemically charge in redox processes. And if you look at cyclical tomogramma, what we can find, there is an overlap of double layer capacitance with a broad but electrochemically reversible redox peak, because the separation between reduction and oxidation peaks is very small, just about 20 millivolt here. What is interesting, the peak stays even if separation increases up to an enormous rate of 100 volts per second. So we charge our device within, say, 10 milliseconds, and we still have redox. What does it practically mean for us? It means that if we have materials with sufficient electronic conductivity, we should be able to design redox-based battery type energy storage devices that are capable of not minutes, but actually seconds, milliseconds even, charge storage using redox mechanisms. What we need electronically, ionically conducting materials, and we need to design the architecture of electrodes, which will provide fast transport through thick electrode films. And in this case, we also can have transfer of electrons to from transition metal atoms, which lead to combination of this double layer and redox energy storage. Moreover, titanium-32, which I showed you, is not the best energy storage material. Theoretically, many other MXenes have been predicted to produce significantly larger storage. But if you work with dilute aqueous electrolyte, if you work with, for example, sulfuric acid or other acidic electrolytes, we're always limited by voltage window. And voltage window determines largely also the amount of energy stored. So what we need to expand the voltage window. One way of doing it is using so-known water in salt electrolyte. For example, highly concentrated, close to 20 molar lithium chloride electrolyte. And what you will see will happen. In this case, we can widen the voltage window from 1 volt for sulfuric acid. This is a curve I showed you before here, to about 1.6 volt, which significantly increases the total amount of energy stored, if we can have also sufficiently large capacitance or current density in this case. However, what is interesting, we observe in this case a couple of peaks now, which are in the range of positive potential. For a typical battery material, one would say, look, it's a reversible redox process. We have two peaks on charge discharge, which are redox. However, what is interesting, when we looked at mechanics brazing of the electrodes, we found that these peaks actually correspond not to conventional redox process. They correspond to ions with solvent being completely removed from between electrode and collapse closure of MXene layers, and after that reinsertion. So when we have processes which express themselves like a battery-like redox in cyclic voltammograms, but in fact are different. Similar differences we observe if we look into organic electrolytes. Some type of a lithium TFSI electrolyte, type of electrolyte used in batteries here. What we found was again that depending on the solvent we use, we can get different electrochemical performances related to either intercalation of electrolyte and solvated ions, like in case of DMSO with lithium, and oscillation of lattice spacing as intercalation, the intercalation happens here. Or much smaller nodes here, 19 angstrom, 13 angstrom. In case of acetonitrile, or just 10.5 angstrom spacing. Take into account that layer of titanium 332 is about 9.5 angstrom. We pretty much have layers which are separated by very, very thin monatomic layer, as we know now, lithium here. So a lot of electrolyte co-intercalating, little electrolyte co-intercalating, no electrolyte co-intercalating. So we can have a case of, like in a battery, just lithium stored between MXenes, or a case like in a supercapacitor, where solvated ions are in between MXenes. So basically, we learn how to control those behaviors here. And a paper which will actually be coming soon in Nature Energy that we produced with several colleagues from several US and European institutions actually shows that in these two-dimensional systems, we can actually, by controlling confinement, move from double layer type capacitive energy storage, like in this cyclic camera shown, to really pretty much battery type energy storage. We just need to learn how to control ions, salvation, redox reactions at the interfaces in confinement in these materials, how to select right combination between the materials and electrolyte. And we believe this offers really exciting opportunities for future developments here. I'm not going to go in specific example today. I just won't have time to do it, particularly since I started my talk 5 minutes later because of problems with logging in here. But what I just wanted to mention that pretty much by now, there are publications, and I only show some of the first papers in this list, and also it's an incomplete list, on exploration of MXenes for electrochemical capacitors, lithium, sodium ion capacitors, all type of ion batteries, lithium, sodium, potassium, magnesium, aluminum, also lithium, sodium, potassium, sulfur batteries. Various type of hydrogen devices, on-chip textile wearables, printable devices, and so on and so forth here. But kind of a warning, if you want to explore use of this very large, virtually infinite family of materials, designer materials, in specific application like energy storage, but the same I can say about water desalination, separation of ions, or evaporative desalination by using photothermal effects. MXenes are very good light to heat converters and absorbers of light. You have to be guided by computational science. You cannot select from huge number of materials just by trial and error or your intuition. You need to go through computation, select materials which are predicted to show the best performance, and also go into applications where they can really make a difference, not just stay in the range of number of other materials, which actually would be a case for lithium-ion battery application active materials. But they really can make a difference in metal sulfur batteries, compensating the high conductivity of MXene for low conductivity of sulfur and strongly adsorbing polysulfide. They can suppress dendrite growth, allowing metal batteries, and also add as current collectors much thinner one. They can enable flexible devices, printable devices on chip. They can be incorporated into fibers and textiles, helping with developing future flexible, transparent, wearable energy storage, but also by the same token harvesting, for example, tank solutions here, or high frequency applications, again, because of this very high ionic and electronic conductivity here. And the last but not least, they can be used in many current devices as passive elements. For example, copper current collector and lithium-ion battery take about 17% of weight. If we can replace them by 3 micron instead of like a 12 micron thicker copper MXene, which will be about 10 times lighter current collector, we can actually decrease the weight of current battery and actually size because of thinner current collectors. We can use them as conducting binders that allow printing from water. They can be used for production of hydrogen as electrocatalysts. Some of them have been shown to be close to platinum by DFT calculations here. But experimentally, they have been shown to actually be very competitive to moly disulfide and other materials here. And they also can be used as support for catalysts, for example, again, for water splitting for single platinum atom catalyst design. There are many, many other applications here, but I want to leave a few minutes for questions. And I know my time is almost finished here. The message I would like to leave you with is here that we have this enormous and very, very quickly growing family of two-dimensional materials with very unusual combination of properties here. I talked today a little bit about potential energy storage applications, but they can be used for reinforcing composites, metal, polymer, ceramic ones here. They are already the best materials for electromagnetic interference shielding, and similarly can be used in printable antennas here. Membranes for water air purification, gas separation, adsorption of toxic heavy elements, sorbents, very important applications. There are many medical applications, sensing, also environmental sensing, portable for technology. And of course, electronic application to such an extent that Hussam Al-Sharif from KAUST already basically announced a new field of electronics, MXetronics, emerging here. Plus catalysis are only touched on HR, but of course other fields here. So, and what is important, because this is scalable chemical synthesis process using solution or emulsion salt chemistry. It's a process that can produce materials not only for small sensor or electronic devices, but also for energy storage and environmental applications here. But of course, there is a lot to explore. Exploration is starting. If you want to read more about MXenes, check our recent review article published in Science last year, which covers in brief properties and applications of those materials. There is already interest from industry emerging, and particularly MXene Association has been created to bring together potential users of MXene materials, developer of MXene products, and researchers working in the field here. And also, if you want to learn more about MXenes, there will be at least 4 conferences this year dedicated to MXenes. There will be 2 symposia at the spring MRS meeting in May in Honolulu dedicated to MXene, and another symposium on MXene at the fall MRS meeting in Boston at the end of November. There will be the 4th International Conference of MXene in China, in Nanjing, on May 18th to the 21st. And at Drexel, we will be organizing for the second time a conference during the first week of August, where we want to go all the way from science to application, bring together business, industry, and researchers working in the field to discuss MXenes here. And this is my very last slide. Of course, all the work I showed today was not done by myself. It was done by excellent students, postdocs in my group. We collaborate with many people, at least 20 different organizations nowadays around the world in many different countries. This is how you solve problems which are interdisciplinary, which are at the cutting edge, particularly in the area of energy storage application. From the very beginning, I was working with Professor Patrice Simon from Paul Sabatier University. You see him on the occasion of being inducted to French Academy of Sciences here. So again, thanks to all the scientists and of course, funding sources that supported our research in the field of MXene. And with this, thanks to you for your attention. I'll be glad to answer questions.
Thank you very much, Professor Yury, for the nice presentation and excellent talk about energy storage that I think is very interesting to everybody. So I will begin with the questions. All right, our first question, is D8 electronic configuration possible in MXenes?
I'm not exactly sure of what you mean, but I would put it this way. MXene inherits their structure from MAX phases, from basically carbides and nitrides. You can also look at them as a 1-1-1 slice of the sodium chloride lattice of carbide or nitride, like titanium carbide bulk here. So it means that if you look at electronic configuration of transition metals in those more traditional bulk materials, you will have pretty much a good idea about MXenes. There are many papers describing electronic structure of MXenes, which I just simply didn't have time to know today. But again, if you go to our review in Science or our publication on our website that you can see here, you will find information about it.
All right, thank you. Another question from BN. The synthesis of MXene is quite critical, and selective etching of A layer is not easy. Also, hydrofluoric acid is very dangerous. What other agents can be used for etching, and what parameters mainly control its synthesis so we succeed in its preparation?
Especially, this is a very important question, especially when we talk at a conference about sustainable technology. First, MXenes were produced using concentrated HF. Pretty much, we use now fluoride salt like sodium fluoride, lithium fluoride can use, and HCl, much milder etching here. And we published just about like a month ago, or a bit more, a paper on chemical safety when synthesizing MAX and MXene in ACS Chemical Health and Safety Journal discussing this issue here. There are emulsion salt methods for etching, which don't include acids at all. Again, when you use fluoride-containing salts and acids, you again decrease the danger here. But developing more benign methods for synthesis of MXene is one of the definitely critical goals for large volume, low-cost synthesis of those materials.
Thank you very much. Another question, how efficient are MXenes and their catalytic performance toward wastewater remediation applications?
Well, again, wastewater remediation is a very, very broad field, definitely. What has been shown for MXenes? MXene can do at least three things. One, You can use them in membrane for separating organic molecules, ions, letting water to go through, because they're hydrophilic and you can potentially control spacing between the layers. MXenes have been shown to be very good solvents for heavy ions like lead, uranium, chromium, others. So they can be used to remove those toxic heavy ions. And again, they have catalytic and photocatalytic properties because of these plasmonic properties in the visible or IR range, and can be used to catalytically destroy organic molecules. So this is another potential application here. There are entire review article written on environmental and catalytic application of MXenes, and I would recommend you to check those reviews.
Okay, thank you. Another question: how these MXenes materials are compared to recent inner venue nickel hydrogen or metal hydrogen batteries?
Well, again, you're compare apples to oranges. MXenes are not batteries. Those are materials for use in energy storage. So if you look into battery design and architecture here, this is where you can replace potentially metals or active materials, anode, cathode materials with MXenes. And this is how we need to look at them here. They add building blocks, possible replacement for metal current collectors to make them thinner, lighter, and printable, say. Replacement for binder and conducting additive at the same time. So similar to graphene, say. They can be used in batteries. They can enable metal batteries because they suppress growth of dendrites. So what it means practically here, researchers who work on battery design, battery architecture, battery chemistries need to be aware of those new materials added to their toolbox and use them where they can effectively replace or complement existing materials.
So if, let us say, if we want to mix them with polymers, how do we see the mechanical behavior? Will it be enhanced or well, how we are going to interact?
Actually, just like 2 days ago, I think on Monday, we published a paper with with Ian Kinlock from Cambridge, from the Graphene Institute, on load transfer from MXene to polymers here. You can mix MXene very effectively with polymers that have some functional groups like carbonyls or amino groups. You can have either strong van der Waals interactions or even covalent bonding. You remember I mentioned possibility of grafting organic molecules, for example, reacting amino groups or electrostatically attracting amines to negatively charged MXene surfaces here. They're actually more forgiving than graphene to large number of layers because strong interaction of MXene, so you don't need to delaminate them completely. And of course, having young moduli in hundreds of gigapascal and mechanical strengths of single flakes at the range of 10, 20, 30 GPa, they clearly can provide very efficient reinforcement for polymer simultaneously with potentially increasing conductivity, dielectric properties, and a number of other characteristics. So definitely exploring MXene polymer composite systems in films and fibers as bulk reinforcement or modifier of properties is a very, very efficient way of bringing them into applications. Yeah.
Thank you. Another question from Dr. Ihsan: why titanium carbide is the most widely MXene structure compared to other MXenes?
Well, it's a very reasonable question here. Fundamentally, there is absolutely no reason for titanium carbide being the best. It's actually a very good MXene because it has titanium and carbon, two elements which are among the most abundant on our planet. So it's the one that can potentially can be produced large quantities. It's economy of scale kicking in with the cost and everything else. It was simply the first one discovered. And so far, the best study. But if you're looking into specific properties, there is no reason to believe it is the best. If you're looking into magnetic, say, properties of chromium, manganese, will give you interesting applications here. If you look into superconductivity, look into niobium. If you look to specific optical properties, you need to basically take different elements which will give you plasma resonance at different wavelengths and different optical properties here. It's again simply the first one and the most studied one.
Okay, thank you. Another question from Mr. Sayed Shaheen. I would like to know the stability of MXene. Chemical and thermodynamic stability are critical challenges for materials used in energy storage applications. In the presence of aqueous electrolytes, the MXene is prone to oxidation. As a result, how should MXene be prepared or regulated to ensure long-term stability?
Very valid question, too. MXenes are metastable materials in environment because they can be oxidized to oxides, and they are more active chemically compared to, say, graphene. Like everything else, it has pros and cons. Pros that you can react them, they're capable of this, say, surface redox and so on. Cons that they can degrade with time. Now, if you take titanium-32, as long as you have proper atomic ratio, so it means that few vacancies in the initial structure, and make quality flakes of MXene again with minimal number of defects. As you can see, for 6 months stored in dilute solution in a closed vial in water, there's no change in Raman spectra. After 10 months, just a couple of pinholes appear in the layers. So if you put it to low temperature storage in high concentrated solution, you can store it basically for months. As soon as you produce it into a film, dry it well, or incorporate into composite material, they probably will be, well, I don't want to stay stable forever, but we have samples which survived many, many years. They still look the same. I have, I'll may even show you a sample of printed 4 years ago. Well, no, I won't show you. I probably put it elsewhere. I had a portrait of Professor Millie Drexel house that my student printed when she passed away. And it's still black, looking exactly the same way as it looked when it was printed on paper here. So they can store for a long time, but you need to be aware of this. Just about 3 months ago, we published a paper on improving stability of V2C, which was considered to be the least stable MXene initially, degrading within a day in solution at room temperature in open here, to at least 4 months storage in solution here. So again, you need to be aware of the fact, but yes, definitely they're more stable than a very large number of other low dimensional materials.
All right, thank you. Another question, are MXene stables under irradiation? Any possible in situ reduction when they combined with semiconductors? From Mr. Hafid.
Under irradiation, you mean, or what?
Yes, yes, under irradiation.
I remember seeing a couple of studies of MXenes exposed to high intensity beams. I don't remember outcome, but I'll put it this way. Look at them as a carbides and nitrides of transition metals. You have strongly bonded metallic atoms. So I would put it this way, in terms of mobility, they're better than metal. Say, break down current for monolayer MXene is about 2 orders of magnitude higher compared to copper, and at the same level as graphene. So the atoms are sitting stronger. If you radiate them, you can kick atoms out of the structure, but again, max phases, their precursors, are considered and explored actually in materials for nuclear safety because they don't really swell much here. So I guess they will be sufficiently resistant, but again, it's outside my personal field of expertise. And I don't think really much has been done on exploring those properties of MXene. And of course, they can be combined with semiconductors, and there are materials semiconducting here. But I would put it this way. There are many semiconducting 2D materials, including, say, the classic molybdisulfide. So I think attractive is using them in combination with known semiconductors as current collectors, making couples when you match a work function, for example, that you can tune in MXene, and so on here. Basically, barrier controlling between the layers here. I think this is applications that are really attractive because there are many applications you can potentially use MXene. You always need to ask yourself a question here. Will it give an advantage compared to the current materials? And use them where they can bring unique advantage. For example, electromagnetic shielding, plasmonic properties, tunable work function, adsorption, surface redox. So those are things where applications of MXenes are really advantageous.
Thank you very much, Dr. Professor Yury, for this nice presentation, very informative and very promising for the future sustainable materials. Thank you again, and I hope you enjoyed the presence, and maybe we'll invite you very soon to Saudi Arabia so we can enjoy.
I will be glad to come and visit again. Slowly it looks like travel restrictions are being lifted. Actually, I came back from Paris yesterday myself. I think it's time for me I've stopped sharing my slide and time to move to the next presentation.
Yeah.
Again, thank you for giving me an opportunity to give this talk online, and I look forward to seeing many of you in person soon.
Thank you very much, and see you soon.
Yeah, and actually I just wanted to mention Professor Bakr on my, I think, last visit to KAUST several years ago already here, and look forward to listening to your talk.
All right.
Thank you, Professor Gogotsi. Thank you.
Thank you very much, Professor Yury. Welcome, Professor Osman Bakr from KAUST. I would like to welcome you here for giving us a nice talk on metal halide perovskite single crystal solar cells from high efficiency to fundamental insights. First of all, I would like to introduce Professor Osman Bakr. He's a professor of material science and engineering at KAUST, Saudi Arabia. He's also an associate editor at ACS Materials Letters. He earned his BSc Material Science from MIT, as well as MS and PhD in Applied Physics from Harvard. His research group works on the design and self-assembly of hybrid and inorganic materials to generate breakthrough applications in solar energy harvesting, photonics, and optoelectronic devices. His group has been at the forefront of the synthesis, property elucidation, and application of two major classes of materials, which are metal halide perovskites and atomically precise metal nanoclusters. Professor Bakr has published more than 247 articles. His group research appeared in premier interdisciplinary publications such as Science, Nature Energy, JACS, Joule, ACS Energy Letters, Advanced Materials, and others. Professor Bakr, he's a fellow of the Royal Society of Chemistry and also the fellow of the Institute of Materials, Minerals, and Mining. He was selected as a member of the editorial advisory board of ACS Energy Letters and Chemistry of Materials. He has been named as one of the 10 leading university researchers worldwide in the field of perovskite solar cells by Times Higher Education. So please welcome with me Professor Osman Bakr to give us a nice talk about metal halide perovskites.
Thank you, Dr. Osman Hamous. And I'd like to thank the organizers. Such an honor here to be today, a pioneer of the field of MXenes, and Professor Omar Yaghi, a pioneer of the field of MOFs. And so I'd like to thank you for including me with such a group of amazing speakers. Today I'll be telling you about another family of materials called perovskites, and I'll be telling you specifically about some of the work we're doing in our group on single crystals, solar cells, and some other things. Before I start, I'd like to thank my students and postdocs who have actually been doing this work, and I'm actually just presenting, and they've been doing all the hard work. And I'd also like to thank my collaborators, because this, just like Professor Gogotsi said, a lot of the good work happens only in collaboration. And I've been lucky enough to have really good collaborators, including at KAUST, such as Professor Omar Mohammed, and outside of KAUST, such as Professor Ted Sargent. And together we've done a lot of work on fundamental materials characterization and application of perovskites in devices, as well as understanding the material at the fundamental level. And I'm very grateful for funding provided, the generous funding that I've received from KAUST, as well as Saudi Aramco and SABIC, and I'd like to thank them for supporting the science that goes on at my group. I'm sure a lot of you have heard about perovskites. Our group works on perovskites, and many of you have heard about solar cells, perovskite solar cells, but actually perovskites have a lot of different applications. Almost every semiconductor application can benefit from perovskites, from LEDs to photodetectors, all the way to even X-ray scintillators and X-ray detectors. So why is that? What makes perovskites very versatile? First, let me tell you a bit about the material itself. Perovskites have this ABX3 formula. They're ionic compounds, where B is in an octahedra of X and A is in the void that's surrounded by the octahedra. And almost 50% of the elements in the periodic table can form a perovskite. They just have to obey the tolerance factor that basically governs the relationship between the radii of A, B, and X. And if that tolerance factor is close to 1, then you're very likely going to form, there's a good chance to form a perovskite structure. These materials have tunable band gaps, very high absorption coefficients, they're very defect tolerant, and the charge carrier diffusion in these materials are long. In addition to traditional perovskites, if you start making the A cation large, you start breaking up the perovskite network, and then you could start forming very interesting two-dimensional materials, for example, or zero-dimensional materials, or one-dimensional materials. And even if you start using surfactants, you could start creating nanocrystals and quantum dots. So we can understand, if we look at the low synthesis temperature for perovskites, because of the formation energies is low, and you look at the different forms of perovskites that we could get, from nanocrystals to single crystals to bulk crystals, and also to different forms of compounds we can get, from zero-dimensional materials to 1 and 2 and 3-dimensional materials. We can understand why perovskite is such a versatile material that can cover a lot of different applications, and we're just discovering some of these applications. A lot of you have heard about perovskites because now its biggest splash at the moment is in the field of solar cells, and perovskites now have exceeded in efficiency single junction silicon, and we're reaching now 25.5% efficiency is the latest. But what it brings is that it's solution processable at low temperatures, and it's compatible with large-scale production methods. So that creates an exciting situation where potentially we have a technology that can really bring value to the energy challenge that our world is facing. My group, so most of the research groups around the world were focused on polycrystalline films and polycrystalline materials, because that's easier to grow. But we wanted to understand the material at a more fundamental level without having to grow single crystal. And it turns out not a lot of groups paid attention to this problem, and it turns out that simple methods that were used by other fields to grow single crystals haven't been applied so much in perovskites. And so we started looking into how to apply perovskite crystallization methods to perovskites. And one of the simplest methods we developed was basically growing perovskites and from a good solution and storing the solution in a bad solvent, and over the matter of a few days to a week, you get diffusion of the bad solvent in the good solvent, the supersaturation of the perovskite solution, and you start seeing a crystal grow. What makes this different, what makes perovskites different, is that the single crystal that grows is actually quite large. Normally, when you grow crystals with this method, you get very tiny crystals. And one of the first things we did was try to estimate the diffusion charge carrier diffusion length. And what surprised us, so we couldn't measure it directly, we had to measure the mobility and the carrier lifetime, and then use the Einstein relationship to estimate the diffusion length. And what surprised us when we measured the diffusion length of single crystals, it turns out they were in the order of tens of microns, and that was about 100 times longer than what people anticipated, what people thought when they were measuring thin films. So that was a big change in the way the field started thinking about perovskites, and they realized that if we improve crystallinity, we could improve the performance of solar cells significantly, and that's what happened actually. But if it took 1 week to grow perovskites, single crystals, is that practical? How can we use crystals that are materials that take a week to grow? And sometimes even if you look at the other classical methods, it can take up to a month to grow. So we started looking at different methods to grow crystals, and by chance we discovered a method that allows us to grow crystals, large crystals, within minutes and sometimes in hours as well. And we call this method inverse temperature crystallization. And it started by a simple observation from one of my students, where they noticed that when you dissolve your perovskites in a coordinating solvent and you start raising the temperature, the perovskites, instead of dissolving more, they started precipitating. And so if you cool down the solution again, you dissolve the perovskites, but if you heat it up, the perovskites precipitate. That's kind of counterintuitive to what you normally would see when you dissolve, for example, sugar in water. When you raise the temperature, more sugar dissolves, not less. Here, the opposite is happening. So this phenomenon is called retrograde solubility. And we notice that it actually occurs for a wide variety of metal halide perovskites in coordinating solvents. And so we see that the solubility drops down when you raise the temperature, and that's because you form in a coordinating solvent, you're forming complexes with your with the metal halide, and when you raise the temperature, you start breaking up these complexes, and you create conditions for supersaturation. So here's an example for a crystal that normally would take a week to grow, and with this method, if you do it very carefully, you can grow your crystals in under supersaturation at a very high rate in a matter of minutes to hours. And what we found is that you could keep repeating this process and you can perpetually keep growing your crystal bigger and bigger. And what was surprising as well for us, it was a tiny observation back then, but we realized it was a very important observation later on, and I'll explain to you why, that we could grow these crystals in the shape of the vessel they form using this method. So whatever vessel we put them in, the crystals take that shape. And I'll show you why that's important. So we showed that this inverse temperature crystallization method is actually quite general and occurs to in most metal halide perovskites, and can be used in to generate many compounds, single crystals of many compounds. So how can we apply single crystals for devices? Bulk single crystals are difficult to integrate in devices because in devices you need very thin crystals. So you either find a way of polishing the crystal and cutting it and or you find a way of growing the crystals thin. With materials as perovskites that are have low formation energy, that are sensitive to many solvents, thin for device applications. And we started looking at how can we control the nucleation and growth. And one of the things we discovered serendipitously was we found that if you introduce a sonication pulse prior to solution supersaturating, you can create a cavitation bubble that spreads the crystal growth on the surface. And so instead of getting a bulk crystal that grows laterally, that grows in thickness, instead you can get a very thin crystal that's a few thousand nanometers in thickness, but millimeters in lateral dimensions. And what that allowed us to do was to study the first single crystal film solar cell. What that showed us is that perovskite single crystal cells are actually relatively stable. And what makes them unstable is actually the different layers that we add, different device layers that react with the perovskite. Then we started looking at how can we advance this field even further. And by chance, one of the really good researchers in the community, Professor Jinsong Huang, found that you can adapt the method we developed for shape-controlled crystal growth, and you can apply it instead to growing crystals between two substrates. And if you have your two substrates are actually one of them is your whole transport material, then you could actually peel that off and you could evaporate your electron transport layer and you could form your crystal. And that was an interesting discovery, and actually led to a relatively good solar cell. However, we thought that if we can control the growth, we can control the interface quality better, we could actually start looking at improving the devices to the level where they could really compete with the best devices out there. And that's what we did. We controlled the interface, we controlled the temperature, and we did the growth at conditions that are oxygen free. And what we found is that actually the solar cells are as good as the best thin film solar cells, but in fact they're almost 100 times thicker. So instead, normally a thin film solar cell would be a few hundred nanometers. This single crystal solar cell is about 20 microns thick. And yet, despite this, the efficiency was really high. We had 21% efficiency even for our first generation of devices. And we started thinking about, so this was a big jump in efficiency of single crystal devices. We started looking at how to improve this further. We found that changing the solvents, we could reduce the crystallization temperature, and that would eliminate the escape or degradation of the crystal during crystallization, and that creates a better interface. And we could improve single crystal device even further, closer to 22%. And what we found is that we started looking at different compositions, and we wanted to shift the band gap of perovskite solar cells closer to the ideal band gap that you have normally in gallium arsenide. Solar cells have close to ideal band gap for single junction solar cells. So we started mixing methyl ammonium and formamidinium ions to try to shift the band gap. And what surprised us is that single crystals have a band gap that when you mix methyl ammonium and formamidinium, that's narrower than pure formamidinium by itself. And so we were able to create, based on band gap engineering and shifting the band gap, we were able to even push the devices even further, closer to the 23% mark. And for inverted type solar cells, this is close. At the time, this was almost a record for these types of solar cells. Okay. Now, what we wanted to understand is why is perovskite single crystals, why are they still behaving so well despite having a large thickness? So we started looking at can we extend the thickness further? So we started controlling the thickness of the layer by controlling the spacing of the crystal. And we started growing crystals that are up to a few hundred microns thick, up to 300 and 400 microns thick. And what we found is that even up to 400 microns, 300, 400 microns, we still had very efficient current collection. Okay, it's only at the really extreme range, at 300 micron range, where the current collection starts dropping and the efficiency starts dropping. But here you have solar cells that are a few hundred micron, that are almost 400 times thicker than than what people normally make, and they still collect current efficiently. And so that surprised us. So that with the work with our colleagues from Swansea, we started modeling the diffusion length, how the electrons diffuse based on thickness of these crystals. And we were able, for the first time, to measure the directly diffusion of of charge carriers in the solar cells, because we were able to control the thickness of the crystal. And by fitting the short circuit current at different thicknesses, the current efficiency at different thicknesses, we were able to actually obtain a very self-consistent estimate of the diffusion length. And we found that this diffusion length was 500 microns, at least for the electrons. So this is a very surprising. It's much longer than what people imagine, and that's what you would expect in the highest quality type of single crystals, like the single crystal silicon. And so that opens up a lot of opportunities potentially for perovskites in X-ray applications or energy applications where you have high energy radiation collection requirements. So, our group did a lot of work on single crystals, and we think there's a huge potential for this field. They're better than polycrystalline films in almost every way, except that they're much more difficult to make. And this is the next challenge that our group is going to be working on, and I hope the community works on, because we can really advance performance of devices by utilizing single crystal solar cells. So I told you a lot about single crystal solar cells. Now I'm just going to tell you quickly about what we did on some nanocrystals. So we're going to nanocrystals based on perovskites. Instead of single crystals, you could make large single crystals. You could make tiny nanocrystals that are single crystalline as well, using either a hot injection method or a anti-solvent method. And you create these nanocrystals that Maxim Kovalenko's group showed are monodispersed and have controllable colors. And so they're exciting because the color is very controllable. You can obtain any color almost in the color gamut, and so that's really good for LED applications. The problem is the material is unstable, and so you need to find the different capping ligands that stabilize the material than the ones that are normally used. And so we started looking at ways of reducing defects and how to prevent the nanocrystals from degrading, and that's what led us to developing surface engineering methods for perovskites. And one of these methods was exchanging the ligands on the surface with alkyl ammonium ligands. That allowed us to mitigate surface acid-base reactions that degrade the surface and obtain a very stable nanocrystalline compound. And we were able to show at the time what was a record LED, blue LED. Now blue and green LEDs are much more advanced perovskites. Their the efficiencies are very high, and they're very exciting at the moment. But at the time, these numbers were quite high, and they were a record. We were also able to show that some of these place exchange concepts that we developed for nanocrystals, we could apply them for solar cells, and we applied them to passivate solar cells, and we were able to obtain record efficiency solar cells for PIN devices. At the time, they were record efficiencies. And they were able to show that these devices can be stabilized. And then the final thing, I just want to tell you something exciting about perovskites that's kind of different than most materials. Perovskites can be, because they have very good luminescence properties, they also have very short lifetime at the same time, and photoluminescence lifetime. So that means you could apply them in applications where you can modulate light at very fast rates. And one of these applications is transmitting data using white light. And we showed that perovskite nanocrystals can be used as phosphors for white light data communication. And we could reach gigabits of data communication at using white light, which was a record for this technology. The last thing I want to show you is that perovskites are actually, as nanocrystals, are excellent scintillators. So they absorb not only visible light and emit visible light, but they actually can absorb X-rays and high energy radiations and convert scintillate into visible light. So what's really nice about this technology is that this is a material that you can solution process at low temperature. You could create very flexible scintillators with multicolors, and opens opportunities for affordable X-ray imaging and radiography for both medical and security applications. So I just want to conclude and tell you that I've shown you very simple methods to create high quality perovskite semiconductors. That's what makes perovskites very special. Very simple methods can be used to create high quality materials, semiconductors. And I've shown you applications for them in solar cells, specifically single crystal solar cells. But I've also shown you that other types of perovskites can be used in exotic applications like X-ray scintillation and data communication as well. And thank you very much for listening and for being here. Thank you.
Thank you very much, Professor Othman, for this nice talk about perovskites. I hope I pronounced it right. I would like to ask a question, which is that you showed us that you can, the crystals that you grow, they dissolve at low temperature, and at high temperature they crystalline, right? They crystallize. So how can we use that in real applications? So if we are talking about solar cells, we have a lot of fluctuation in temperature. So how stable these crystals will be if we are going through that? So
actually, this is just a crystallization method, and perovskites have an issue, obviously, with at high temperature because their formation energy is low. You could form them very easily and at low temperatures, but because also their formation energy is low, that means you have to live with the fact that they're relatively unstable, and high temperatures. Some environmental agents can end up degrading the system. But for crystallization, if you're crystallizing from a coordinating solvent, then you could end up inducing crystallization by raising the temperature. And typically, we're talking about temperatures that go all the way from 50 degrees to 100 degrees. The advantage is that it's easier to control the growth of a crystal when the crystal growth is being induced by raising the temperature rather than by cooling the temperature. It's always easier to raise the temperature than to control the cooling rate. And so that's the advantage. And what we've shown is, I think the first step is that the community has shown that you can use this approach to actually grow single crystals, and the crystals, you grow them into devices by crystallizing them in this inverse temperature crystallization approach.
Thank you very much. I think we can conclude our symposium for this day. Thank you very much, professors, for being here and enriching us on how innovative materials can be sustainable and can sustainable our future also, and sustainable our lives. So thank you very much again for being with us. And I think there is one question from Abir. Do you have any recommendation to use nanotechnology to treat solar cells? Professor Othman?
I'm not sure how to answer this question, but I think a lot of the solar. So we have a lot of issues with solar when it comes to on the surface treatments. So, for example, anti-reflection is a big issue, and nanomaterials are and nanotechnology, nanomaterials are very important in anti-reflection surface coatings. And as well as surface treatments of interfaces to reduce defects. And I think there's a lot of opportunity there to use nanoparticles, nanocrystals, and even actually, by the way, recently, our colleague Professor Hussam Sharif used MXenes, same MXenes Professor Gogotsi introduced as different transport layers in perovskite solar cells. So really, there is a lot of space to enhance.
Thank you very much for giving us this.
Performance, enhance of these devices by.
Thank you very much. Thank you very much again. I hope you enjoyed the talks today, everybody, and I would like to welcome you tomorrow for even more on innovative materials for a sustainable future. Tomorrow, our session will begin at 2 o'clock with Professor Matthias Spiller. Then we will have Dr. Ashraf Ali and Dr. Bashir Dabbousi. Also, later in the day at 6 o'clock, we will have another session with Professor Pidong Yang from Berkeley, Yusuf Mabhout from Hamad VI Polytechnic University, and Muzahar Hussein from KFUPM. Thank you again, everybody, for attending this symposium, and I hope that you have learned a lot. We have also learned a lot from these beautiful talks by these distinguished speakers, and hope to see you tomorrow. Thank you again, and I hope to see you tomorrow. Wassalamu alaikum.